Hello Math 1093, this is Dr. P with Uninhibited Growth. There's actually no pun in that title whatsoever. I thought I'd do one video where the title was not a joke or a pun of some kind. Actually, this is a problem about a population model. A population grows according to this exponential function, 28,000 times e to the 0.027t, where t is the number of years after 2000. Now, a little side note here, I asked some questions about this function. But the first thing that I should say is that this question, at some level, is completely unrealistic. Populations don't grow according to exponential models forever. I mean, they might for a very short amount of time, or grow approximately according to an exponential model. But the situation described here is what the book calls uninhibited growth, meaning that there is never any factor that limits the growth of this population. Now, in real life, a population that grows for long enough is going to reach some kind of carrying capacity, and it's going to exceed the resources that the environment has to offer, at which point the growth usually tapers off. But in this case, we're going to talk about a population that just straight up keeps growing forever, and apparently it does that for at least 15 years. Okay, so we're going to learn to work with this type of model. You might learn to work with a different type of model, like a logistic model, which is usually more realistic, in another course. All right, but let's talk about, according to this model, what was the population in 2015? Okay, so part A, population in 2015. So we want to find P of 15, because this T represents the number of years after 2000. Okay, so we want P of 15, and that's going to be 28,000 times e to the 0.027 times 15. And now I'm going to use my calculator to figure out what that is. Now, when you use your calculator and you're using the e to the x button, keep in mind that you need to put that entire exponent in parentheses. I think a lot of calculators do that by default, but I just wanted to make sure that was known. Okay, so we're looking for 28,000 times e to the 0.027 times 15. Okay, according to my calculator, that is 41,980.47. Okay, it's like half of a person there. I don't think it's possible to have half of a person except for that one time. Well, anyway, let's just round that to 41,980. That's probably much more precise than it's reasonable to be anyway. 41,980 people. Okay, in 2015. All right, so that's one of the easier types of problems that we can do with exponential functions, is just here's the input, or here's something related to the input, and we put that into our function formula. Okay, now we're going to do something a little bit tougher. We're going to figure out how long it would take for the population to reach a specified value. So when will the population reach 80,000? So we're looking for a time. Let me write this down. Okay, looking for a time for the value of t when P of t equals 80,000. All right, but we're given a formula for P of t. That formula is 28,000 times e to the 0.027t, and we want all of that to equal 80,000, and we want to find what the value of t is when that occurs. So to do this, we're going to divide both sides by 28,000, get e to the 0.027t equals 80,000 over 28,000. And really, each of those contains a factor of 1,000, so I could just reduce this to 80 over 28. Okay, and then I have, okay, so I have e to the 0.027t equals 80 over 28. All right, enough stalling. Now it's time to do like the most important step of the whole process. This t is trapped inside of an exponential function. The way that I get it out is I unpack this exponential function using its inverse, which is a logarithm. In this case, I'm going to use the base e logarithm, or natural log, because I've got an exponential to the base e. But I've got to do that to both sides. Both sides I need to take the natural log of 80 over 28. And notice when I do this, I'm taking the natural log of the entire right side, not of little pieces. I'm not saying natural log 80 over natural log 28. Natural log of the entire right side. Okay, so anyway, now I have a natural log and an exponential. Those two processes cancel out, and I'm left with 0.027t equals natural log of 80 over 28. Notice I'm taking my time when it comes to actually calculating stuff. I'm going to calculate everything at the end so that there's no intermediate rounding involved. So I believe that t is equal to natural log of 80 over 28 over 0.027. And let's find out what that's equal to. Let's use my calculator. Natural log 80 over 28 over 0.027. That comes out to 38.88. Let's just round that to 38.9. So 38.9 years. Okay, now the question asks, when will the population reach 80,000? So I think the answer is 38.9 years after 2000. So I guess probably sometime in the year 2038. Okay, I guess it kind of depends on what we mean after 2000. Does that mean like after the start of 2000? I don't know. If we mean after the start of 2000, then 38.9 years later is not going to be quite 39 years later, so it would be sometime in the year 2038. Okay, so now finally let's talk about the percent growth rate of the population. I'm just going to move up here so I have a little bit more room to work. What is the percent growth rate? So this is actually something I want to kind of explore here. There's a way of reading it off the formula, but I just want to do some calculations here. All right, so let's keep track of what the population is at various times. All right, and I'm going to keep track of the year just using values of t. So I'm going to put 0, and I'm going to put 1 out here, but I want to do actually some smaller measurements. I want to do like 0.1 and then 0.01. Okay, and then population I'm going to put here. And then I want to keep track of what was the percentage growth from year 0. Okay? And then finally, I'm going to keep track of what was the percent growth per year. Okay, this is kind of a complicated table here. All right, so anyway, in year 0, what is my population? Remember, my function was P of t equals 28,000 times e to the 0.027t. I'm going to use that for all these calculations. So now, my population at year 0, well, that's just the initial value of this function. That's 28,000. I can read that right off. If you don't trust me, then actually substitute t equals 0 in here. Realize that this exponent becomes a 0. It's like a big 0, e to the big red 0 there. And then 28,000 times e to the 0 is just 28,000. So the population at year 0 is 28,000. Now I'm just going to quickly do all the remaining calculations of population so that we can focus on calculating percent growth. All right, after some repeated calculator usage, I got the following values. For t equals 1, I got 28,766.30. There we go. For 0.1, for t equals 0.1, I got 28,075.70. And for 0.01, I got 28,007.56. Now you're probably wondering at this point, didn't we just talk about how there's no such thing as a fraction of a person? So why is Dr. Patterson putting all of this stuff in the table, all these fractions? And the reason I'm doing that is because I'm really looking for insight about how this model works, not just about how many people there are at this point. So I'm putting those fractions in because they're an important part of the calculation. All right, so now I'm going to calculate the percent growth. Now, in case you don't remember from high school science class how to calculate percent growth or percent change is usually calculated as the change in the value. So in this case, the change in the population over the initial value. That is the value at the start of the time that you're calculating the percent change over. So in this case, we're going to do P of t minus P of 0. That's the change in population over the initial value, which is P of 0. Okay, so we're not going to keep track of percent growth here because that's the initial population. But we are going to keep track of percent growth for all the others. So here, the percent growth at year 1 is going to be 766.3 over the initial population, 28,000. What does that come out to? That should be 766.3 over 28,000. That's 2.737%. 2.737%. Okay, now I'm going to redo this with this next value. At t equals 0.1, I got a change of 75.7 over 28,000. And that comes out to Okay, it's 0.2704%. All right, and finally, what about this 28007.56? So that's a change of 7.56 people, whatever that means, over 28,000. And that comes out to exactly 0.027% according to my calculator. Okay, now what does all this mean? Well, if 2.737 is my percent growth over the course of 1 year, then that means I'm growing at a rate of 2.737% per year. Here I have a growth rate of 0.2704%, but that is over just 1/10 of a year. So that's 0.2704% over 0.1 years. That comes out to 2.704% per year. Okay, because I'm growing by this percent over 1/10 of a year, so I'll just scale that up by 10 in order to get the percent growth per year. And finally, if I have 0.027% growth over 1/100th of a year, then I take that, I divide by 0.01 year, and I get exactly 2.7% per year. Now, when I say exactly, I should be a little bit careful because there were some other decimal places here that I left off of this. But down to a few decimal places, I get exactly 2.7% per year. Now, where is that? Where could we find that 2.7%? Anywhere in the formula over here. My formula was over here. Do you notice anything that looks like 2.7%? Ah, there it is. Okay, so the moral of this story is that if I give you a formula that's P of t equals some initial value times e to some coefficient times t, that coefficient represents either a percent growth rate or a percent decay rate. And I would say that's per year, but it's not necessarily per year. It's per whatever the unit for t is. Sometimes t will be expressed in days, sometimes in hours, and whatever that is, that dictates what the percent growth rate or decay rate is with respect to. So that can be read right off the formula. I could have just looked at that and told you that the growth rate was 2.7% per year. But to see that, we had to actually do these calculations and see that, okay, over 1 year, we're actually getting 2.737% growth. But if you look at a very microscopic level, what you see really does look like 2.7% growth per year. All right, anyway, that's the end of that. That was kind of a long one. Sorry about that. But I always get kind of excited about these formulas. People always wonder why this E here is such a special number. E is a special number because this idea of how to read the percent growth rate or the percent decay rate, this whole thing, and now I actually want to emphasize this even though I'm now like over 13 minutes. Okay, sorry, I meant to do that in a different color. That didn't seem to work out very well. Okay, this idea of how to read the percent growth rate or percent decay rate, this only works when the base is E. That's what's so magical about that number. The initial value bit I can do no matter what the base is. Like I could have a power of 2 or a power of 14 here, and the initial value would still be 28,000. But that coefficient only tells us the growth or decay rate if the base is E. Okay, that's the end of this video. Thank you.